Okay, get ready for a wild one. What if the fundamental particles that make up our entire world, things like electrons, aren't tiny little points at all? What if they're actually tiny knotted up filaments of energy? Today we're diving into a fascinating new theory that has an idea so out there it could completely flip how we see reality itself.
But to really get a handle on this new idea, first we have to go back. We've got to tackle one of the oldest and, frankly, one of the weirdest puzzles in all of physics: wave-particle duality. Seriously, this mystery has been keeping scientists up at night for more than 100 years.
And this is the question at the absolute heart of quantum mechanics. I mean, it just sounds impossible, right? Like something straight out of science fiction. But experiment after experiment shows that on the tiniest scales, particles seem to pull off this incredible feat all the time. The classic experiment that proves it, it's called the double slit.
Now, the result of this experiment is what's truly bizarre. You'd think if you fire a single electron at a wall with two little slits in it, it's got to go through one or the other. Simple. But nope, that is not what happens. Even when you send them one by one, the electrons build up a pattern on the screen behind the slits as if each one was a wave that somehow passed through both slits at the same time and interfered with itself. How is that even possible?
So how in the world can we explain this? Well, a new theory called Swirl-String theory, or SST for short, proposes a surprisingly physical picture, something you can actually visualize. It gives us a whole new way to think about the electron, and it all comes down to a really simple analogy: a hula hoop and a knot. So here's the core idea. SST says an electron isn't a dimensionless dot. It's not a tiny marble. Instead, picture it as a tiny little string of swirling energy. And the crucial insight, the real game changer here, is that this string isn't static. It can exist in two completely different shapes, or phases, and that's what explains its bizarre dual nature.
And these are the two states. On one hand, you have its wave-like phase. In this form, the electron is an unknotted, spread-out loop of energy. The theory calls it a ring. But when it acts like a particle, that very same string gets twisted up into a tight, localized knot, specifically a trefoil knot. It's the same fundamental string, just in two totally different configurations.
This quote right here, from the paper summary, gives us that perfect mental image. Just think of the wave-like electron as a relaxed, spinning hula hoop. It's spread out, it's floppy, it can ripple. Now imagine twisting that hula hoop up into a tight, compact knot. All of its energy is now concentrated in one tiny spot, and just like that, it's become a particle.
Okay, so this brings up a really obvious question. If the electron can be either a smooth, wavy ring or a tight little knot, what actually causes it to switch from one form to the other?
Right. What's the trigger? What provides the energy to take that smooth, spread-out hula hoop and wrench it into a bunched-up, particle-like knot? Well, the theory doesn't just wave its hands here. It offers a very specific answer. The answer is an interaction. To be specific, an interaction with a single photon that is just the perfect, precise, resonant frequency. When a photon with exactly the right amount of energy smacks into that ring, it drives a transition, forcing the string to collapse from its spread-out, wave-like state into its compact, particle-like knot. All right, so now we have all the pieces of the puzzle. We've got the electron as a string, we have its two states, the ring and the knot, and we have the photon trigger that flips it between them. So let's go all the way back to that original mystery, the double-slit experiment, and see how this new framework explains everything. Okay, first up, the unobserved experiment, the one where we're not looking. According to SST, the electron starts its journey as a delocalized ring, or hula hoop. Because it's all spread out, it literally passes through both slits at the exact same time. The two parts of the ring then ripple and interfere with each other on the other side. It's only when this rippling ring finally hits the detection screen that the interactions force it to collapse into a localized knot, leaving that single dot. But what happens when we try to watch which slit it goes through? Well, our detector, which uses photons to see, interacts with the electron before it even reaches the slits. That photon forces an early collapse. The ring becomes a knot right then and there. And this knotted-up particle, well, it can only go through one slit or the other. And with nothing to interfere with itself, that beautiful wave pattern, it just vanishes. And this is exactly what experiments show, time and time again. This chart basically visualizes that relationship. Fringe visibility is just a fancy way of saying how clear the wave interference pattern is. And as you can see, the more strongly you monitor the slits, which really just means you're hitting it with more photons, the more that pattern gets destroyed.
Weak monitoring lets the ring state do its wave thing, while strong monitoring forces an early collapse into a knot and poof, the pattern is gone.
This table just sums it all up perfectly. When it's traveling, it's a ring, acting like a wave, creating interference. When it's detected, it collapses to a knot, acting like a particle, making a dot. And if you try to measure it mid-flight, you just cause an early knotting, which kills the wave behavior. It's a remarkably clean and elegant solution to a century-old problem.
But you know, as cool and intuitive as this idea is, a compelling story just isn't enough in science. For swirl string theory to be taken seriously, it has to do a lot more than just explain an old mystery. It has to make new predictions that we can actually go out and test in a laboratory.
And that is the absolute key. This isn't just some neat philosophical interpretation, it's a falsifiable theory. And what that means is that it makes specific, concrete predictions that, if they're proven wrong, would disprove the entire idea. This is what makes it real science. This is what separates it from just, making up stories.
And here are just some of those predictions. The theory says we should be able to find new, never-before-seen lines in the light that atoms absorb. It predicts very specific energy shifts in these giant puffy atoms called Rydberg atoms. It even suggests we could use a special kind of laser to essentially flip the interference pattern on and off whenever we want. These are real, tangible experiments that physicists can now go out and try to perform.
So, this whole theory leaves us with a truly profound question to chew on. The paper suggests these knots form out of something called a universal swirl condensate that fills all of space. So, if an electron is just one type of knot in this fundamental swirl, what other particles could be other, more complex knots? It suggests that maybe the entire particle zoo, maybe reality itself is all just topology, just different kinds of knots tied in the fundamental fabric of existence.